So this is our second example. F of x equals 3x squared. Again, it's a degree 2. And 2x squared plus 3x minus 2. So again, it's a degree 2. So we're going to do the long division to rewrite this one with a fractional part, the degree of the numerator less than the degree of the denominator. So here I did the long division and ignore that part. It was just a tiny calculation. Turns out the quotient is 3 over 2. The remainder is this negative 13 over 2 x plus 2. That's the remainder you see down there. So if you put it into this form where the horizontal asymptote is obvious, and that's how it's going to be, that quotient appeared here, and the remainder appeared as a numerators of this standard form. So it's a slightly more complicated numerator we end up at than the example earlier. And this is the slightly more simplified version. So what I did is that because this 13 over 2 looked too bulky, so I factored out 1/2 from the numerator. So that negative 1/2 was factored out, and negative 13x remains there, and this 2 changes to negative 4, as you can see here, because I factored out a negative here. Okay? So organize a little bit different so that you can see that's the horizontal asymptotes. So we have this horizontal asymptotes, y equals 3 over 2. So I copy down this expression over here again to analyze whether it's coming from above or coming from below. So here's how you look at it, that 3 over 2 is exactly the copy the same here, and negative 1/2 is just a number out there. I'm looking at this part here as x approaches positive infinity. It's not quite showing here. Now showing as x approaches positive infinity, what happened to this numerator and denominator, and there's additional factor of negative 1/2. Because it's odd degree, and odd degree both positive monic coefficients, so therefore it picks up positive here. But there was this negative 1/2, therefore altogether this one will be a negative number. That's why I wrote this 3 over 2 with a little bit below information. So it's going to approach this 1.5 below that horizontal asymptote 1.5, y equals 1.5. So here's analysis when it is approaching to the negative infinity. If you look at this expression here again, this negative infinity here, well, because it's a 13x over there, that's odd degree polynomial up there. If you think about n behavior odd polynomial as x approaching negative infinity, that approaches negative infinity, right? So that's odd behavior, remember? So that picks up negative infinity, negative number there. And denominators even, so therefore that picks up positive. Doesn't matter if you're approaching positive infinity, negative infinity, because the degree down here is even, so this is going to be positive. So altogether this time works out as a positive number. So it kind of shook a little bit, so I summarized it here. If as x approaches to positive infinity, where is it positive infinity, we saw that it's approaching below. So that's why I wrote it here below, and also sketched the picture right here that is coming from below. When x is approaching negative infinity, we saw that here is coming from above. So when approaching negative infinity is toward to that direction, it's coming from the top. So these are what you see to the left end, and this is what you're going to see to the right end. This part is for vertical asymptotes. You know the vertical asymptote is coming from the denominator part, and we need to factor the denominator. So I factored it here, the numerator, nothing happened to the numerator, but when I factored it, the first factor is 2x minus 1, and second factor is x plus 2, so that must be expanded to this denominator. Once it's factored in this way, it's easy to read these zeros in the denominator. X equals negative 2 and x equals positive 1/2. So there are two vertical asymptotes. One usually don't write down when there's an additional factor in the numerator, but it's possible sometimes that the numerator in it, it had sometimes x plus 2 as a factor. So when you cancel it, and although it's undefined at x equals negative 2, if the numerator has a factor x plus 2 as well, then it's undefined, but you can cancel it. The behavior around it is not vertical asymptotic at all. So we pretty much assume here when we write rational functions like this, it is the lowest term, so that it does not have a factor in between each other. So we assume that the factors you see here, there's no cancellation with the factors you see up there, therefore this is really the vertical asymptotes. But in this form, it's not a factored form. From this, you can't conclude that you actually have to try to factor this polynomial, so make sure that you don't have a factor that appeared in the denominator. So this is the same thing like we did in the earlier example, that if we choose this one vertical asymptote, x equals negative 2, and think about what's happening around x equals negative 2. That's the meaning of this wiggly symbol, not exactly negative 2. But this is a factor is responsible for the extreme behavior, so you leave that factor alone, and everything else is replaced with x value negative 2. So 3 times negative 2 squared, negative 2 times negative 2, negative 1, that should be positive 1. It should be negative 1. I hope I did the rest of the calculation correct, but let's see what happened. So I think that changed a little bit. Instead of adding 1, I have to subtract 1 to subtract 2. I think is the correct answer there is 15. But you probably remember what we care about this number here is the sign, whether positive or negative, so that we can determine the behavior of the vertical asymptotes, as you can see over here. So we still got the positive number despite the mistake in here, so we get this behavior still correct. So here I'm doing the calculation for the other vertical asymptotes, x equals 1/2. So this is the part, 2x plus 1 is the factor is responsible for that extreme behavior. So everything else is replaced with this 1/2 everywhere to see if that's a positive number. Rest of the part is positive number. Then it behaves just like usual odd degree rational function. So it turns out the numerator is the negative number and the denominator is a positive number. Altogether, okay, there's another thing that turns out it's a negative number, and this should be the opposite behavior. It's reflected behavior. So let's see. Again, despite that mistake, is sketched correctly. That whole thing is a negative number, therefore it shows this behavior. If this were positive, this one will go up and the other part will go down. That's the behavior around x equals positive 1/2. So we have figured out the behavior around these two vertical asymptotes and the horizontal asymptote before, so I'm going to put all of them together. So here's a collection. This is the behavior around x equals 1/2. We continue here. This is the behavior x equals negative 1/2. It's kind of the same thing. And to the right, we have this horizontal asymptote behavior, and to the left, this is the behavior. So we're going to try to put this all together by first sketching these two vertical asymptotes and horizontal asymptote. Remember, they are the same number, 1.5, but they approach in slightly different fashion. So this is the picture that I just used just this information to sketch the graph of a function, where I did not actually calculate this x-intercept here, that part here, and that part there, and y-intercept. I did not calculate those, so I ignore that part and just try to put this end behavior together. So these are the two vertical asymptotes, and there's a single horizontal asymptote. So you can see that this behavior to the right is in agreement with this one. To the left is with that one. So these two things are put together. It's interesting. So because it's going down like this, it's going to be consistent with what's happening to the right of x equals 1/2, which is what you see here. And to the left, it has to go up, so I started from here. But if you look at what's happening to the right of -2, that must be this behavior right there. So I have to come down, and if you just copy that behavior to the right of x equals -2, this is kind of reasonable shape that you can imagine they're nicely connected to, and not making anything complicated. So to the left is above behavior, the horizontal asymptotes. That's why I have this shape there. And to the left of x equals -2, you can see this is going up there. So I put that up shape up there. So altogether, this is the simplest shape you can come up with, putting this all 4n behavior together. But again, I'm not sure if these x-intercept and y-intercepts are correct, but this is the first attempt toward it. In the next part, I calculated x and y-intercept, so resketch it with an accurate x and y-intercept. But overall, shape looks like this. So in this part, I'm trying to calculate x and y-intercept, so I copied the polynomial down again. So let's do x-intercept first. So x-intercept takes place when y is less than 0, so I wrote it down. So y is represented by this rational expression. When this rational expression here is a 0, only the numerator is 0 and denominator is non-zero. That's the only possibility. Or you can set this one equal to 0 like this and multiply both sides by the denominator, and then you can see that cancels this denominator here, and whatever you multiply to the right hand side is a 0. So this whole thing equal to 0 is the same as the only numerator set equal to 0. So if you can solve this equation, that'll be the answer. So it has happened to have a nice factorization. If not, you have to use a quadratic formula. So that factorization is a 3x plus 1 and x minus 1 equal to 0. That's the factorization. So we have two x-intercepts. Those are namely x equals -1/3. They came from this linear factor. X equals 1. They came from that linear factor. So we have these two x-intercepts. So let's figure out a y-intercept. Y-intercept is when x is equal to 0. So when x is equal to 0, you simply go ahead and plug in x equal to 0 to this expression. So it's usually, when we're looking at this function, computing y-intercept is fairly simple. Just plug in x equals 0. But x-intercept here for the function, usually you end up as solving equation because you're setting this whole thing equal to 0. So usually computing x-intercept is more involved than computing y-intercept. So we're just simply plugging in f of 0, x equals 0 to the function f of 0. So that knocks down everything here. So only left with -1 divided by -2. That's a positive 1/2. So as you can see, we have exactly the same shape of the graph, and this time I put those x-intercept and y-intercept in a correct position. So x-intercept 1 appeared here, and y-intercept -1/3 appeared there. Sorry, the other x-intercept and y-intercept, the positive 1/2, is located here. So when this middle portion is going through, it actually passes through these two portions. That gives us a pretty good idea about where this one is located. So that's a better sketch than before.